All right, let's talk about a mystery that's been costing the AI world millions. We're talking about these incredibly advanced AI models. You pour a fortune into training them, and then, seemingly out of nowhere, they just collapse. They fail, catastrophically. But what's really wild about this whole story? The solution? It's shockingly simple and was right under everyone's noses the whole time. So I want you to imagine this for a second. You're in charge of training one of these giant language models. You're feeding it just tons of data, using up massive amounts of computer power. Everything's looking good, the model's learning, it's getting smarter, and then boom, it just hits a wall. The performance doesn't just dip, it completely collapses. So why? Why does this happen? That's the question, and it's literally a multi-million-dollar one. Okay, so to get to the bottom of this, we've got to look at something called reinforcement learning fine-tuning. Now, don't let the name scare you. Just think of it like the final coaching an AI gets to really sharpen its skills. You know, like an Olympic athlete who's already great but needs that last bit of coaching to perfect their technique. It's super powerful for making an AI better at reasoning. But, and this is a big but, the process is just notoriously unstable. It's super sensitive and causes massive headaches for the people building these things. And yeah, we're not talking about some rare one in a million bug here. This happens all the time. It's this frequent, super frustrating and incredibly expensive problem. The whole industry has been scrambling to figure out how to make this training process more stable. Because, every single time one of these models goes down, you have to start all over again. That's weeks of work and just a ton of money completely down the drain. So where do you even start looking for the culprit? Well, naturally, everyone's first suspect was the most complicated part of the whole setup, the algorithms themselves. I mean, it makes sense, right? You figure there has to be some deep, complicated bug hiding somewhere in all that code. And the prime suspect had a name: Training-Inference Mismatch. Here's the best way to think about it. AI systems basically have two different modes. You've got training mode. That's the gym, it's practice, it's where the AI learns. Then you've got inference mode. That's game day, when it's actually out there doing its job, generating answers. Now here's the kicker. Even though these two modes are supposed to be mathematically the exact same, tiny little differences in the software and hardware mean they end up with slightly different results. And everyone thought this tiny gap between practice and game day was the thing causing all the chaos. So this theory led to a whole bunch of really complicated, really clever algorithmic fixes. Researchers built all these fancy patches trying to account for that mismatch. But they were all just red herrings. It was like putting a Band-Aid on a huge gash. Yeah, it might help for a little while, but it wasn't fixing the real problem. And even worse, these fixes often created new issues, like making the training painfully slow. The AI would take way, way longer to get good at its job. And get this, these fixes weren't cheap. Not at all. To make them work, you had to add this whole extra computational step, which jacked up the already insane training cost by about 25%. Think about that. You're paying a massive premium for a solution that doesn't even really solve the problem. Okay, so if the complex algorithms were a dead end, where did the real breakthrough come from? Well, this is the cool part. The answer came from going back to basics, like the most basic component of computing, the numbers. The researchers decided to just forget the algorithms for a minute and look at the actual format of the numbers the computer was using. See, in the world of AI, when you're dealing with these 16-bit numbers, you've basically got two main contenders. First, there's BF16. This is the industry standard, the one everybody uses. Think of it as the flashy, popular rookie. It can handle a massive range of numbers, from teeny tiny to huge, but it's a little sloppy, not very precise. And then you have FP16. This one's like the overlooked veteran. Its range isn't as big, but its precision, it's tack sharp, way, way higher. And the real difference maker here is something called manticipits. That's the part that really determines the precision. So FP16 uses 10 bits for this, while the standard BF16 only uses 7. Now, I know, 3 bits doesn't sound like a lot, right? But in computing, that's a huge deal. Those 3 little bits give FP16 8 times more precision. 8 times! And right there, that's the smoking gun. The researchers in the paper lay it out plain and simple. BF16, the industry standard, is the main culprit. They figured out that its low precision was causing these tiny, almost invisible rounding errors. And over millions and millions of calculations, these tiny errors started to add up. They snowballed, getting bigger and bigger, until that gap between the practice mode and the game day mode grew so wide that the whole system just fell apart. So just how big was this difference we're talking about? Well, they ran the numbers, and the mismatch between the two modes was a whopping 24 times larger when they used the standard BF16 compared to FP16. 24 times. So think about what that means. The problem was never some hidden bug in the code. It was a feature of the number format that literally everyone had decided to use. So, after all that time spent digging through complex algorithms, the real root of the problem turned out to be so much simpler. It was hiding in plain sight, in the very foundation of how the computer was counting. And because the problem was simple, the solution was, well, it was beautiful. No more complicated patches, no 25% cost increase. It was just one single line of code. All they had to do was switch from the sloppy BF16 format to the super precise FP16. That's it, a one-line fix for a problem that was costing millions. And the results? They were just night and day. The researchers ran what they called a sanity test on a problem they knew could be solved perfectly. And look at this. The simple algorithm, just using the precise FP16, got to 99% accuracy, practically perfect. Now look at the other guys, the fancy complex fixes using the standard BF16. They topped out at 95% and then became unstable. And the basic algorithm on BF16, it couldn't even get past 84% before it just completely collapsed. It's not even close. And this wasn't some fluke either. They tested this everywhere. On those complex mixture of experts models, FP16 was way more stable. What about for LoRa fine-tuning? The BF16 version collapsed, while the FP16 one trained perfectly. And for the big dense models, FP16 was faster and just performed better. I mean, the evidence was just overwhelming. Case closed. So what does this all mean for the future of building AI? Well, I think it's a really powerful lesson, right? It's a reminder that sometimes you have to step away from the super complex stuff and just go back and check your most basic assumptions. And the big takeaway is this: you've got to use the right tool for the job. See, BF16 became the standard for a good reason. Its huge range is fantastic for that first big initial training phase of a model. But when it comes to the much more delicate, sensitive process of fine-tuning, well, for that job, precision is king, and range just doesn't matter as much. The industry default, it just wasn't the right tool for this part of the job. So let's just wrap up the key points here. Number one, those mysterious AI collapses, it wasn't some crazy algorithm bug. It was just a problem of bad precision. Number two, a simple one-line code change to FP16 works way better than all those expensive, complicated fixes. And this stability, it just leads to faster training and better models in the end. And maybe the biggest lesson of all, you should always question the default settings. Don't just assume they're the best for what you're doing. And it really leaves you with a bigger question, doesn't it? I mean, this whole story is just a perfect example of how sometimes we get so obsessed with finding a complicated answer that we totally miss this simple solution that's been staring us in the face. It really makes you wonder, what other huge, unsolvable problems out there, in tech or anywhere really, are just waiting for someone to challenge a simple, basic assumption that we've all just accepted as true.